One, 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 one,
Are you hearing us? Yes. Cool.
one.
Yeah,
Is it working?
Yeah, it's working.
Okay.
Do we
I'm
need to raise the volume? Ladies and gentlemen, can you hear Oleg?
111. Hello everyone.
fine.
Is it good enough?
Yes.
Okay, perfect.
All right. Hello, everyone. I'm the one who sent you that email along with all the hairy discussions that we get into development channel about reactive programming. My name is Volkan. This is my friend Oleg. He will already have his official introduction, so I will skip that part. So we have been, I think, digitally meeting with each other in the last 1.5, 2 years, something like that, in the Twitter rants and GitHub tickets. So he's one of those reactive guys. He's actively contributing to Project Reactor or any project that has a notion of reactive in its README. So he was kind enough to come here. By the way, he will be presenting tonight in Reactive Amsterdam meetup. And in addition to that, he will be presenting also in the JFall that is upcoming on Thursday. And he was also kind enough to come here and make a presentation for us too. This won't be a repetition of what is going to take place. So please give him a warm applause, and it's all yours.
Hello, hello, hello. And first of all, thank you for finding a time. Your lunchtime is important, and you decided to kind of exchange it on something interesting, I hope. And welcome you to this presentation about the state of reactive streams. And first of all, thank you, Volkan, for inviting me. I'm just propose that I'm open to do anything, and Volkan kindly say, yes, I'm gonna organize something for you. So thank you, Volkan, for doing that. It's my pleasure to be in such a great company. And yeah, I know that you're building great e-commerce business, biggest e-commerce business in Europe. So it's my pleasure to stay here and explaining you some interesting things about reactive programming, reactive streams, and the state of all of those technologies. So are you ready? Perfect, let's start. So my name is Oleg, I'm from Kiev, from Ukraine. Have you ever been there? Actually, if you have never been there, you are welcome to visit Davox Ukraine, which I'm part of. And in any other case, you are welcome to visit Kiev. It's a great city. I'm reactive guy. I'm doing reactive programming and reactive streams and all of reactive things on the daily basis. I was and I'm still contributor of Project Reactor, and I'm improving that project besides my daily duties. And today I'm working for Natify, where we are working on our socket. This is a future of reactive streams and reactive programming, but this is later. So, in general, let's talk a little bit what you're gonna learn during this presentation. So, basically this presentation is more about philosophy. It's not that technically in depth, but you're open to ask any questions related to reactive programming, reactive streams, reactor, and I'm more than happy to help you with that. But today, first of all, we are going to start with the state of reactive streams, and we are going to figure out what was the history behind this technology, how it evolved, and what it ended up today. Then we are going to understand what is the state. And finally, we will figure out what is the future of all of this cool technology afterwards. So this is the plan. Is it sounds good? Yes. Perfect. So let's start. Everything, all this reactive is about interaction, which means that there is components, there is environment, there is everything, there is a system which should interact with other components, with other environment, and should change its state. And the first kind of mentioning of reactive in the history was actually about reactive system. And it was in 1985 in the paper on the development of reactive system. And here reactive is about the system and the type of the system which reacts to all of the possible events continuously, like over the time without stopping. So the main question is, what is the difference between non-reactive and reactive system then, right? And I'm gonna, the main character of for us today is Goose. Have you ever heard about Goose before? No? All right, one person. So goose is basically duck, but it's like more eastern part, Europe, like who is speaking in Russian, they know what is goose. But in general, the goose is our person. And you can imagine that there is a goose, like a system, to whom everyone just trying to push some events, commands, and everything. So do that, do this, do nothing, or you are not allowed to do that. So non-reactive goose will basically ignore everything and say, what? What do you say? I'm not interested in that. The only thing in which this type of birds are interested is basically food, and you know what they produce afterwards, yeah? So this is kind of non-reactive goose, and basically non-reactive goose is interested in food. It cares less about everything else, and it just cares how to get more food and produce the result of it. So in contrast, reactive goose would change its state for every event. So it's gonna react to this, then to that, to this and that and this, and afterwards it will change its state continuously, depends on the event which came to it. So basically reactive system is a system which continuously changes its behavior, depends on what happened before. So that's the idea, and it reacts immediately, like timely to everything. For example, your service is not available. Then another service gonna change state, like enable circuit breaker, for example, and will not continue request in this particular instance. So this is reactive system. All right, it seems cool, but our talk is about reactive programming, and we will get back later to reactive system, and we will see how reactive system kind of mirror it and reflect it on reactive programming. But anyways, reactive programming started a little bit later, like 5 years later, and it was in the story of reactive programming started with UI. You may wonder why. Basically, because at this point in time started competition between Macintosh and Windows for user interface kind of audience. And the idea was to build really responsive UI for doing for moving icons and windows and everything like in timely manner. So what is the problem then? The problem is that we have to have a proper set of technology which let us build in responsive UI. So let me show a small demo in order to explain what I mean. So you know that we have to have ability to move windows like this, right? Responsively without any lagging, and it should just work. When we click expand, it should magically animate and take the whole window. So you can imagine 19s, what did they have? Basically nothing. They just started building UI, and the simplest that they ended up is something like that. Yeah, this is kind of responsive UI they got. And that's kind of UI no one wanna experience, right? We wanna use really responsive and smooth dragging and so forth and so on. So if you're gonna look at what kind of code we can write, you will see that basically we need a function which let us transform, which let us react to something. For example, someone gonna click the button and then started dragging things, and we have to build some behaviors, depends on that. And the simplest the engineer could do with the API available at this point in time is to create, for example, a queue for all incoming events, and then periodically check them with some interval, for example, right? For example, every few seconds check what's happened, and then build some behaviors depends on that. Yeah, because of that, of course, we got the problem that some events happened later, and we process them in sequentially, and we just keep all the movements, and that's the problem. But anyways, that's the mechanism. Of course, we can speed up or improve the frequency of looping, and it improved the state of our animation. It will be much better. Yeah, I hope it's gonna reload. Yeah, it became better, but you can imagine what kind of hardware we had at this point in time. A single processor, just 64 kilobytes of memory for everyone, and you can imagine that you are spinning your CPU every millisecond. So any other program are not able to do anything because you just took the whole CPU processing time, which also a problem. So either it's slow or inefficient. All right. let's go back to our slides, and we see clear problem that we have to have some mechanism. And actually, in 1991, 92, the window exposed an API, like they announced that they are having like event-driven reactive API inside the Windows. And basically what they proposed a little bit later were called as observer pattern. Have you ever heard about observer pattern before? Great, everyone, that's perfect. So this was an innovation that Windows proposed, and basically it turned the building of user interfaces dramatically. So let me show you another demo. And now, instead of using pooling or pooling check-in model for new events, we will start reacting to them immediately once the event appears. So that was the idea of observer pattern. Instead of check-in, the observer will be notified once event is appeared. And what happened? Let's check. Basically happened the good thing. It started working smoothly as we wish. That was the idea. And if you're gonna look at the API, we still have the same functions, we still have the same logic, but now API let us set some listeners or observers to particular set of events and react to them immediately. And then hardware implement the particular things which let us do that without any kind of overwhelming or any overhead. So that was the idea. Basically, we are using observer pattern, and now our UI works pretty well, which is good. So that was kind of approved by Goose, and everything started working pretty well, and it seems okay, looks good. So what else do we need? But there was a but in the word, because later in the time we got requirement to build somewhat a little bit more complex, which depends on the event or even from user side, like clicking or movement. And from one point of view, it looks like, okay, easy, right? But in fact, it was a little bit more complex. So every developer ended up with something like that. And yeah, we ended up with what we ended up, and yeah, we got that code. So what kind of problematic we got afterwards? Basically, we started building more complex processing because we had to like somehow react to mouse movement, build another reaction, depends on that, and so forth and so on. Then it appeared that we have to build some animations like this kind of Windows movement and so forth and so on. So that have to be also built into the system, and developing of such things have to be pretty transparent. So using just plain observer pattern led to increasing the complexity of the code and losing the clearness of what we wrote. So we got some problems, and actually we found a solution a little bit later. In 1997, Connell Elliott, which was one of the engineers at graphic team at Microsoft again, decided to build something much better, decided to combine some functional and reactive things for functional. So this is the second place where reactive words appeared. And basically the idea of reactive animation or functional reactive animation was to provide some DSL set of structures, functional kind of writing of code in order to just quickly explain what you want to have. And afterwards it led to building some really complex animations like this, which depends on your movements and other events in the system, which was really easy and straightforward. So that was cool. Basically, let's summarize this part of the history. First of all, observer pattern became a technique for building UI efficiently in push model. And then a little bit later, in order to solve a little bit more complex problems, functional reactive animation appeared and started solving much more complex engineering problems. All right, sounds good, but 2000 or new millennium appeared. And what do you remember about 2000? Any ideas? What changed basically? Any thoughts, friends? Yeah, basically our communication turned in a little bit different direction. instead of doing communication within a single hardware or a single computer, we built TCP and we started using TCP in order to connect different systems. And the requirement of doing communication over TCP appeared. So basically the problematic of new era or new millennium or 2000 is, in order to build efficient network communication, we have to have a proper tool for that. And let me show what I mean, because you may wonder, so what's wrong with just simple request-response communication? So what else should we invent? Let me show you that. All right, let's go back to our main application, and let me show you plain one-to-one communication. And yeah, let me switch to our UI, and yeah, let me pause it for a second and explain what's going on this screen first. So here is the emulation application, which shows communication between client and server or client and database. It could be whatever, just two different computers. And here is some controller of what's going on the in our emulation. So this is basically time here, which says how long it lasts. This communication between client and server. This is basically a button which let me fuse and fuse, and this is the speed of the whole process, so I can control the time. And a part of that, here I have some number of elements which I have to process at the bottom. So you can imagine that your client have to filter some number of elements or have to display them somewhere, and it goes to database, take some elements and get back, right? So this is a normal communication which we are doing for a while. So basically, before, when we hadn't any kind of limits, we were doing communication within one hardware, and we got an assumption that everything happens immediately, right? We was thinking that if we're gonna call something, for example, memory, it happens immediately. Then, because of that, we built system which just doing request response. And it was good. Like, it was pretty good when there were nothing. But then once we turned into network communication, one thing appeared. Which one? Right, latency. The latency appeared, and the latency and the communication over the network is not immediate, happens immediately, which brings more problems. So let me introduce to our system a few more characteristics. For example, latency. Let's put that sending a packet over the network takes, for example, 1 second. So how it turns? Basically, it turns into really bad communication. So you can see that in order to process the same number of elements, now we have to spend some time. And it's not just a couple of seconds, it's just a couple of minutes. And if I'm gonna increase the speed, we will have to wait for a minute as well. But yeah, we are not going to do that because this is just wasteful. It's clear we have a problem in communication, right? So what we can do? One of the options is, okay, if all the data is here, let's bring them there. And instead of running over the network, let's just run one query, collect them all, and put in the cache. That's one of the options, right? So it's called give me all, for example. Give me all pattern. So people started using this pattern in order to bring all the data. And it seems pretty efficient. So let me just, yeah, we collected all the data. We had to wait for a while the database collected them. And then we sent it over the network. And then we just super fast processed them. Really efficient communication pattern, even faster than one-to-one in the single application. So it took 6 or 7 seconds for doing processing. However, there is however. What kind of however do we have? Can we just put everything in our single application? For example, it's fine if we have like a few megabytes of data. But what about a few gigabytes of data? Or terabytes? Can we put them all in one single machine? No, we can't. So basically, every machine, every hardware has its limitation in terms of resources, in terms of memory, in terms of disk, in terms of everything. So basically, we have to put these kind of constraints in our system, and we have to say that our memory capacity is not limited. A part of that, the network bandwidth is not unlimited as well, because we can't just push a terabyte of packets or terabyte packet size and it will be flashed immediately. No, it doesn't work like that. It will be split into several packets or several thousand of packets, and we have to feed them into a single machine as well, somehow into a single network connection as well. For example, we have network throughput in 23 magical items. It doesn't matter, it's just abstract items. So the communication will turn that, yeah, we have to find all, and then what we found have to be split onto several packets, like the first packet, and then the second, and then the last one, and then the processing will take a little bit more, because in order to start processing, we have to wait for the whole body, like you're requesting the array of JSON, and then you have to wait for the whole body in order to start parsing that JSON and not the other way around. So we have to wait. And then if we're gonna put some, for example, memory limits, we will see that, yeah, we have, okay, this is Russian word, but basically this is memory. So this is memory, yeah, I forgot to translate it, but anyways, it's memory. So basically, here we go, we put everything into the memory. So, for example, our memory capacity is 23 elements, which is fine, but once the next packet appeared, the out of memory happened and our system crashed, because we can't just expand our memory immediately like as it's elastic. No, it doesn't work like this. We have to fit what we have, and we have to fit our data into our limits. So basically what we can do, how we can avoid this problem? Any idea? You're doing that every day, guys. So basically, maybe instead of trying to fit everything into our memory, we can just ask for some limited number of elements, for some batch of data, right? So this is another kind of technique. Instead of requesting everything, we can say, okay, give me some batch, give me some portion of data, and we're going to process them and then request for another batch of data. So it can work. So let's see how it, in which direction it turns. And basically, yeah, we requested for a batch of data, the database generated it, and we started processing. So we started processing, we spent some time, and then we requested for another batch of data. So we are saying, give me another portion. And database returned it, we fit into the memory because we exactly know that we are requesting 23 magical element, and we started processing them. And then we can request for another batch if we need more elements, but in any case it takes a little bit more, right? 9 seconds instead of 6 seconds, which was the baseline for our communication. Which means, all right, we have problems and it's still inefficient because we are doing too many network hops. All right, let's go back and let's do some summary of what we saw. Basically, the downside of this period of time is that pulling one-to-one model, which was the main pattern of doing things in the previous generation of software engineering, is not efficient. The network has its limit, like bandwidth, and the hardware is not like elastic. It's limited by size, by number of something. So we can't just put everything on our computer and ignore anything else. So we have limits, and basically that problem appeared in 2000s at Microsoft. So Eric Meyer with the team was thinking how to build their Azure, because at this period of time they just started building Azure, and they have to build like microservices or service-oriented system which had to send lots of data between each other, between each components, between different databases, and somehow it should work fast. So that was the question. And after some thinking on the problem, Eric Meyer said, Erica, I know what to do. Let's apply observer pattern. And instead of pulling, let's push data, as it was at UI. So he took like the simplest pattern ever. He applied observer pattern, and it turns in the following direction. So instead of pulling or requesting for data, he said, okay, let's just say the system to push data. And then we're going to process them one by one as it appeared. because every element takes some time to process. So once we found one, we can just immediately flush it and then start finding another and flush it. And at the same time, yeah, I'm gonna show it. It will be much better. So I'm gonna show what happened. Basically, streaming happened, and yeah, let me slow down it a little bit. So elements started looking like the lookup for elements started happen ongoing. So we found one, we started sending that element to the network, which means that only a couple of elements in the network, and we know the speed of elements lookup. So network bandwidth probably won't be overwhelmed, and nobody will be stuck in the network. And at the same time, the latency is the first feedback between communication between client and server is much higher or much lower, latency much lower. So the client can start processing data almost when the first element came in, so which is also much more efficient, and we don't have to wait for the whole batch, which is much better. And it turned that the whole processing time took much less time than it was even for all elements, which is much better. Do you see that? So which is great. So basically, what he've done is he applied the push pattern instead of pull pattern. However, there was a however. This observer pattern, we have the same problem: how to write clean and transparent and readable and simple code for doing business logic. And basically, that was a problem because, on the one hand, we had one observer pattern which let us efficiently push data in a synchronous manner. However, with this pattern, we don't have any understanding where is the end of the stream, because data is not endless, so we have some end of the data stream, and we can't just simply unsubscribe in observer pattern. This is another limitation of observer pattern. We have no clue how to say, okay, stop, don't send data anymore. We've done what we had to do, and we don't need any more data, so please cancel the subscription. There was no option to do that. On the other hand, we always worked with some representation of stream like iterable, right? Or iterator. You all know what is iterator, right? Perfect. So iterator let us efficiently iterate over the set of or stream of elements. Of course, it's a little bit inefficient because we have to say, okay, give me next, give me next, give me next, which is basically pull pattern. However, it's clear where is the end because we are checking has next, do you have next, do you have next? And we always know how to close the iterable because there is this part of pattern as well. So we can close the iterator and say, okay, we don't need this stream anymore, please release the resources, which is pretty good. So basically what Eric Mayer done, he said, okay, let's apply these two patterns together. Let's use what was before, like reactive animations, because you remember that reactive animation was some programming paradigm or language or DSL for building complex transformation for events. So he applied all of these things together and got reactive extensions. And basically reactive extensions, or RX, is combination of observer plus iterator, and then it appeared that there is three other interfaces like observable, which is source of data. There is observer, which right now follows the iterator methods, kind of iterator methods like on next, on error, on complete. And here, on error and complete, clearly say that this is the end of the stream. And we have subscription, which let us cancel data. So we solved all the problems by combination of those two patterns, like async data push, clear way to say, to understand where is the end, and clear way to unsubscribe. So the problem solved, plus we got the DSL from like in reactive animation, like functional declarative way to process the stream of asynchronous items independent from each other. And it turned that this was so cool, so it appeared in other programming languages even far from C#, because initially it was developed at .NET, and .NET was pretty good for doing that. There was super flexible. And after releasing of RX.NET, this paradigm like spread at other programming languages as well. And the most coolest part that everyone just followed the same set of DSL or operators. So in JavaScript, we got the same map, flat map, filter, whatever. In Java, we got the same set of operators. Even in Swift, we got the same set of operators. So one reactive programming engineer can do everywhere and everything in the same way, which was super cool. So the final summary for that, it seems that we are done. What else do we have to improve? Because we have efficient data streaming over RX with cool programming paradigm, and development of complex data processing pipelines now works pretty well, and engineering problems solved. What else do we need? So basically it seemed pretty enough, but there is but again. And the problem was that we consider it only a part of communication patterns. I mean, we consider it the case, let me run it again, when producer is pretty fast, consumer is even more faster. You can see that consumer consumes data pretty efficient. That's why memory is pretty stable. So we are not, we process element and then we throw it away if we don't have to keep it in the memory, or we just keep a couple of them. So it's ongoing real-time data processing, which takes a little bit of resources. And because consumer is pretty fast, nothing wrong happens. But it appeared that sometimes consumer can be slow, right? Producer can be fast. However, speed of consumer can be really slow because it processes, for example, I don't know, the hash of Bitcoin, just in case. So there is another case when we have slow consumer and fast producer. So let's try to simulate it and figure out what happened. So basically, I have two configurations here, like lookup of item, lookup time, and processing time. So this is another two configurations. And now processing time is much higher, like almost 5 times higher than producer speed. So, and in this case, let's see how our interaction turns out. Bow. That's what happened, basically, because slow consumer just consume data, put them in the memory, and fast producer just produce data, and there is no way to say from the consumer side that we are not ready, please don't send us, we are full of memory, like in terms of items, so we are good to just process what we have. And there is no such mechanism to do that kind of communication, which started being a problem in 2012, 13, 14. So basically, it wasn't super cool solution as it turned out. So what kind of problematic we got at this point in time? First of all, slow producer, fast consumer communication case, which led to crash because of memory outage. And then it turned that the programming paradigm is implemented, like the set of operators is pretty same. However, the behaviors from language, from implementation to implementation is totally different. So RxJS works in this way. However, RxJava works in a different way because we have multi-threading. And Rx, for example, for Objective-C works in another way. And one single engineer knowing all these solutions can just simply start using another without looking into the internals. And then how we can combine different implementation even in the single system, because there is no standardized way to say, okay, this is my RxJS and this is my Akka streams, how we can easily combine that without introducing some adapters. There wasn't a way to do that because it was just a set of class which is pretty incompatible with each other. So we got another set of problems and solution appeared again. In 2013, actually it started in 2013, the set of engineers from Pivotal, from Twitter, from Netflix, from many other big companies decided to gather together because they all built the same things, the same reactive libraries, and they decided to standardize that. And then they decided to put the part of communication pattern between client and server in order to preserve stability between publisher and subscriber. So what they basically invented? Basically they invented the same Rx plus batching. Because we remember, in order to fit everything in memory, we applied pattern batching before. So why not to use it here? And instead of kind of synchronous batching, apply asynchronous batching and request for data asynchronously and then receive them in the same streaming way. So that was basically the idea. And basically, that was the idea behind reactive streams. So a part of that, they invented 4 interfaces. Instead of classes, they invented 4 interfaces, like publisher with method subscribe, the same observable. Then subscriber, the same observer, but with one additional method on subscribe. And basically, publisher started sending to subscriber over on subscribe method subscription, which now got not a single cancel method, but request method, which basically a contract or contract between publisher and subscriber for doing asynchronous batching. And basically now subscriber was able to say, okay, give me 10 elements asynchronously, and then it received those 10 elements and not more. So that turned the communication. And it solved like the same push model, which was efficient, plus it added asynchronous batching, which became kind of pull-in communication. So right now reactive streams is kind of mix between push and pull model. And then it standardized a set of interface which solved the problem of different implementations compatibility. So let me show you the demo and let me show how it turned out. Right now we are going, so we are keeping the same set of configurations, slow consumer, fast producer, and now we are applying reactive streams instead. And let's see how it's gonna work. So basically, right now, in order to let publisher send data, we have to say, give me the number of elements. And in this case, we are sending the particular number, like give me 23, because we know that the memory capacity is 23 items. So the first is give me some data request. Let me slow down it a little bit. And afterwards, the producer will produce exactly the number of elements we requested and not more. We will see that by memory filling. Here we go. Then we are slowly processing them. We are spending some time on doing data processing. Let's increase it a little bit. So we are processing, and then we are seeing that we are about to finish the processing. We processed, for example, 18 or 15 elements. So it means that we can do some math, calculate what time takes requesting elements from here, generating, and we can calculate how much time will take to process it to the end, so we can efficiently request another batch of data before we end it with the current one. So we will always have some data to process. We will efficiently make load on the database, and it will be much better and much more stable. So do you see the case? And it's pretty efficient. Yeah, it's much efficient in terms of time for taking processing, but yeah, it's pretty good. Even though if we can like roll back the configurations to initial, we will see that it works pretty fast as well. So now we have fast producer, now producer send data, and we can see that even this previous configuration takes 5 seconds. The RX took, for example, 4. Good? Pretty good. So it was another way to do stable and efficient data streaming using now push-pull mechanism. All right, what happens nowadays? Because that's basically what we have right now, and this type of specification we are using nowadays. And it turns that the adoption went really well, and we are having reactive stream specification for C#, we are having reactive stream specification for JavaScript, and we are having reactive stream specification for Java. The same set of standardized interface with the same set of specified rules, which is good. And it turned that the adoption of library became really well as well. We got Akka streams for Scala, we got reactive for .NET, we got Project Reactor. How many Project Reactor users we have here? Okay, not many, but anyways. RX Java users? Oh yeah, Project Reactor wins, that's good. And we have Reactor.js. Even in JavaScript, we have its own reactive library, a part of just RxJS, which is pretty good. And it turned to really popular kind of adoption. And a part of that, like, they wrote a, yeah, let me show a different thing. And it turns in the like more coolest direction, because the adoption of reactive streams started being a part of JDK, and now starting from JDK 9, we can easily use reactive streams and set of mentioned interfaces and get all these benefits, not moving away from JDK, which is great. So it started being a really cool solution, and it found adoption everywhere, even in Java, in standardized set of libraries, which is pretty good and means something, right? So let's summarize what we saw. Basically, reactive stream specification started a standard for asynchronous data streaming with stability as a first-class citizen, and we can do whatever we want with pretty high efficiency, which is pretty good. However, there was a but again. And it seems, what can go wrong? We solved everything. But we have to remember another problematic, which we are. Because we are software engineers, we are developers, and we don't want to solve any problems. We want to just try another framework, right? So that's true about us. And basically, it seems pretty good. Like, when everyone started using reactive programming, for example, they wrote map, take, filter, then they've started writing flat map, another flat map, and then a couple of shoots in the lag happened because of another flat map in the flat map in the flat map. So basically that became a problem because of internal complexity and understanding the paradigm and so forth and so on, and especially in Java, everyone started calling block just because try to process elements in imperative programming, which is not working like that. So basically the problems appears in the internal complexity of understanding this paradigm. And instead of trying to solve them to educate ourselves, we decided, all right, let's go back to imperative programming and let's make it great again. And instead of using functional declarative paradigm, it appeared that it could be easy to provide some keywords, like for imperative programming language, in order to switch asynchronous data communication, which requires function, into imperative one. For example, using async await. Have you ever heard about async await before? So basically, this is a way in programming languages to say, okay, I want to call something asynchronous, but I don't want to create functions. So please, programming language internals, create some state machine and move it away, and when the response appeared, please continue execution. That's the idea, like to split parts of your execution, which from one point of view was pretty good and innovative idea. On the other hand, it had some problem. On the other hand, it had some problems. And basically, it turns out that this could be a replacement for reactive programming and reactive streams. And in 2012, a guy from the network asked, okay, is reactive programming and RxJS.NET alive at all, and whether we have a continuation of development here? And the official answer from one of the maintainer of Rx.NET and Java in general was, okay, yeah, we are continue doing work. However, we have already invented a replacement, even for streaming, which got a name async enumerable. And basically, if you're gonna look at async enumerable, you will find out that this is a way to process infinite stream of asynchronous elements, which is another way to do that, but in an imperative way. So what does it mean, basically? You can imagine code like this, which looks pretty imperative, right? So it's pretty imperative code. So what we have here, basically we are opening an enumerator, or async iterator, let's call it, and then we are trying to iterate using the same pattern we get used to for many years, like while, and instead of just blocking the thread, we say, okay, await. So the state machine happens under the hood and it makes magic, and then once the element appear, we start checking the element or pulling the element from memory here, instead of doing like remote requests. And then we can pull, and once it like get off, or we are out of elements here, we can say, okay, let's break this loop and wait again for new elements. So this is a way to process the same asynchronous data stream in a pretty efficient imperative paradigm way, which sounds like a solution for everything, and we don't have to use reactive programming and reactive streams anymore. So it appeared that this paradigm became so cool that it started being a part of Kotlin, of JavaScript, of C#, and recently we heard that there is something similar in Java. For example, most of you heard about Project Loom. And the idea of Project Loom is to brought green threads and the same asynchronous just pulling programming into Java, and get rid of all these reactive things and simplify the life of every Java developer, for example. So it become the great question. So what is the future of reactive programming and reactive streams then, once we get, for example, Project Loom in Java? In order to figure out what is the answer, we have to figure out what is the trends where we are moving today, what direction of engineering we have today. And one of the direction, for example, in Java and JVM world is Graal VM. Have you ever heard about Graal VM before? Yeah, so those who have never heard about this, there is two parts of Graal. There is just-in-time compilator, which is pretty efficient and good, and everyone should just use it because it's built in partially in JDK 9+, and there is some commercial stuff, which is another thing. But apart of that, there is some truffle VM or truffle API, which basically let any languages to be run on top of Java or JVM, which makes another thing to happen, because now we have to ask a good question. What happened with async await once we try to run JavaScript with their async await, or C# with their async await, or whatever other languages with their async await, even Java with Project Loom, in one ecosystem, like in one JVM, and this project with Graal and with Truffle, it's possible to connect them all and start interacting between different environments as it is one ecosystem. So now we can send some data from JavaScript, receive them in Java and send them to C#, for example. And now the question, what's gonna happen? How our system going to behave once we're gonna call async await function? What happened to, for example, our JVM application or to another application which has no clue about async await? Then there is, of course, there is some standardized way of doing async await in C#. There is state machine which is specified. There is another specification for Java. There is another for JavaScript. But how they going to be work together? That's a good question, and there is no answer for that, because we don't know at which thread it's going to be run, which behavior, with which guarantee is it going to be run. And of course, in order to do such communication, we have to have standard, right? Like reactive streams. And this is literally standard. If you're gonna Google for it, just simply reactive streams, you will find out that there is a spec and there is a web page for that. And everything is explained in this spec. So if you're gonna open it, you will see that there is a pretty intensive set of rules, like for publisher, and there is explanation of guarantees that reactive streams gives you, like serial data streaming and thread safe and happens before. All these guarantees appeared here and provided by this specification. And all the implementation should follow it. Either it's Java or JavaScript or C#. So it works in the same way everywhere, which is pretty good and pretty predictable. So it means that standard will work everywhere, and standard and specification will be the same specification everywhere. And someone from Java architects say that power is in specifications, right? For everything in JVM we have specification in JEP. So it means that something specified will be much more better than something unspecified. For example, let me show you a demo of what I said, of doing communication between JavaScript and Java, for example. So let me show you a simple application. So here I have like application, Java application. This is Java. You can see that the extension is Java. So Java, no magic. And here we have like the normal way to build this app. And here we have project reactor in it. So we are using Flux in order to do some stuff, to run it in parallel just in case. And we have another stream. So you can imagine that for some cases, we decided to move from Node.js to Java, or other way around. We decided to have, for example, Node proxy and run some legacy code from JDK that we had before without rewriting it to Node. Or we are trying to use the parallelization mechanism in Java in order to simplify our life in JavaScript. So for some cases, we can use in JavaScript Java features, right? And we want to like explore them and use them in a full power. And let me show you another part of our application, which is this part. So basically, now we are running, we can try to run everything in Graal, and we can easily access to our demo application, which we just compiled, for example, into jar from JavaScript, and we can use classes and everything in order to, for example, do some work. And now, since do work returns flux, it means that it will be reactive streams with the same behaviors as in JavaScript reactive streams. And for example, we can write an adapter just in case, because there is not that good implementation for JavaScript so far, like Project Reactor for JavaScript is not that good, so I try to avoid it. And instead I can use, for example, RxJS with some smart adapter for doing back pressure, and I can subscribe to it and, for example, say, okay, I want to take 10 elements, I want to do anything I want, and then I can process it, right? So let me show you what I'm saying. Basically, here is the app. Let me write clear, and let me explain what's going on. Basically, I'm running Graal Node.js. This is one of the implementation of Graal with Truffle for Node.js replacement. And now this magic thing can bring some jar libraries or jar files into the environment and put it together like here. And then I can say, okay, run it in node mode and run my JavaScript file afterwards. So this is the JavaScript file I just compiled from TypeScript, because yeah, I'm not a dynamic language guy. I prefer like static typing. And once I run it, you will see that here we go. Reactive streams and reactive programming appeared, and my Java application sent some elements and logged out them, and then my JavaScript application also logged out them. So let me show you, for example, to ensure you that this is not a fake element, and I'm saying, okay, console log, I got element in node from Java. So this is what happened, and now I'm adding this element, or I'm logging this element, and now I have to recompile it, because this is TypeScript. Yeah, you have to recompile it all the time. So it recompiled. There is some errors, but it doesn't matter because it's JavaScript, so it's fine. Whatever. And now I'm going to rerun the same app. So the same app, the same. Do you see this? This is the same app. Rerun it, and now got element in node from Java. So it means that I'm receiving stream of elements from Java in JavaScript, which is amazing. And now I can use Java features in order to work in JavaScript, and with same guarantees and with the same behaviors. All right, let's go back, and let's turn into different direction. Because, you know, okay, that's cool, but how many of you are doing the same? I know that there is just a few companies like Wix, and there is Yandex, which are trying to adopt this kind of programming paradigm and communication between different environments. However, most of us are doing microservices and network communication, so how can I use the power of reactive streams of the network? And there is an answer even for that. We are building RSocket. Basically, RSocket is the same reactive streams as a network protocol, which are adopted at many languages, which let you use any transport you want and preserve the same reactive streams guarantees and behaviors. So let me show another demo for you. So in this case, the same Graal, so I'm having the same jar file, the same Node.js application, and browser in addition. So this is another file. So let me show you. The same app, the same Graal environment, but now I'm running RSocket here and exposing as a server some port. And now if someone gonna say, okay, give me a stream, I will return a stream of data from my Java application, from do simple work in this case. Yeah, do you see that? So this is the same app, this is the same demo application, but now I'm calling do simple work, which I'm having here. Okay, where is that? Yeah, simple work, just plain range. And now let me run this stuff again. Let me run it. So I'm running right now this RSocket app. Basically, RSocket app is a client. So it's RSocket client, and now I'm requesting some stream of data from here once I connect it to the server. So this is client. This is server, which exposed me RSocket server, and now I'm connecting and trying to communicate from browser to server. So let me run this stuff and show you that it works. Basically, I have to command this. I don't need it anymore. And I have to, I have to go there. Everything is happened at console right now. So, oh yeah, I have to run it, of course, for sure. I have to run it. Yeah, I'm running right now growl rsocket. Do you see that? Growl rsocket. So this is a different app, but it uses the same growl and the same set of jars. So it's running right now, and now I'm connecting, and here we go. I got 10 elements. Okay, it doesn't work. So I got 10 elements. I connected and I got 10 elements. Even so, I have 1,000 of them. So you may wonder why. Basically, if you're gonna look at the internals of my application, so let me go back here, you will see that I receive, I'm subscribing, I'm exposing the API, and here I'm receiving subscription, which has like cancel and request method from reactive streams. And now I can easily switch it to request 100, and it recompiles but anyways, I received 100. So there is back pressure, and even I can do the following. I can put it into some field, like into some global field, for example, window subscription, just in case, in order to expose the received subscription to the world. And okay, I have to do probably something like this because it's TypeScript, and it won't let me do anything I want. But in any case, I can do something like this, and now I can do this. I can put it into my variable and do any magic I want. So now it's recompiling. So it's recompiling, nothing happens. Anyways, okay, it says that there is an error, so let's quickly take a look at that. Yeah, right, thank you. Thank you a lot for helping. That saved us. Yeah, it's compiled, nothing happens, and now I'm saying subscription my, and I'm saying request 1. Magic. Request 100. Magic. 1,000. Magic, done. That's how back pressure works everywhere. All right, let me go back and do some summary. So is there a future in general? Can we use reactive streams? I guess there is to answer for that, and we have to understand where we are going to apply it, because there is different cases. And in order to understand where to apply it, we have to look at Goose Coop. Basically, it's not a goose, it's a joke. It's written at Eric Mayer white paper. Mouse is your database. You can find the link at the bottom. But in any case, what Eric Mayer proposed is the cube, where there is a different edges. And one of the edges is volume, is the data you're trying to send over the network. Another is your SLAs or velocity. You need really high speed data sending, or it's fine with slow latency, like with higher latency. And there is variety, which means a different type of your data. There is some constraints, or it's like distributed system where every table is absolutely independent from each other, so it's basically kind of key value pairs. And now, understanding our setup, we can easily figure out what kind of technology we can use for that. And basically, at the top of this corner is async await, because it's basically pull mechanism. It's request response in efficient asynchronous way. But again, we can use it for some small number of data. We can use it not for high speed and low latency. And of course, we can apply it for some relational database. But if you want a high speed, if you want to send like a ton of data, gigabytes or terabytes of elements from one to another system, probably we will want to use reactive streams and reactive extensions, which is just a push model with no limitations. However, if we're gonna build stable, flexible system which works here and there depending on our SLAs and requirements for stability, we can use reactive streams, because this is mix of pull-push mechanism, and we can control data speed and whatever we want really easy without rebuilding the system. And it works pretty everywhere with the same behaviors, so we can use it for tuning what we want to build then. All right, This is the final summary. So the evolution of reactive streams started at the really long time ago in 19s. It appeared that the first use case was UI. However, it turned out it found a place in the enterprise world as well. Finally, it grew into some standard and specification. And of course, standard is a standard. It works everywhere. So we can use it for particular use cases or everywhere, but we have to take a look at some cube proposed by Eric Mayer in order to figure out what the use case fits better for us. All right, basically that's it. Thank you for your attention. If you got any questions, I'm still here. All the credits for Goose is on the top link because it's not my art, it's art from particular person. But anyways, that's it. Thank you for your attention, and ask me whenever or whatever you want right now.
I can imagine that you also, like some people might have meetings. That is fine. We will be here. Oleg also will be speaking in our Tech Lab podcast. So we need to be there at 2 p.m. So we have something like a 1 hour, but as you can imagine, we also need to eat something. So, but go ahead. If you have any particular questions, the last time he was okay with it. So. Any questions? Anyone? Totally mesmerized? Okay.
That's also fine. So if you have any questions related to Project Reactor or any questions, just I'm still there and I'm open to anything. Oh yeah, there is one question. Sorry, say it again. Oh, so the question is related to debuggability, right? And how to solve that? How can we address it? Basically, yeah, of course, reactive streams and all these reactive libraries are complex. That's why we got this period of time where we wanted to go with them, and we wanted to use, for example, Async, which is a little bit more easier from understanding, from debugging, and so forth and so on. However, nowadays, like for example, for Reactor, there is a set of cool tools like Reactor block count. Have you ever heard about block count in order to track blocks? So you can imagine that you are leading the software engineering team, and every engineer is different in skills, and someone calls block, another calls in different methods. But we have to avoid it because this is like avoiding blocking is the main benefit of reactive programming. And basically, this tool from Sergey Egorov solved this problem. It basically let you, during your test or whatever process, enable it. It's a Java agent, and it lets you to track what thread blocking is called during the execution. For example, you can mark that this track should be non-blocking, and that should be non-blocking, and this here it's allowed to call blocking. But tuning this stuff, you can easily find out where there is blocks, and then you can fix them. You can say, okay, you don't have to use blocking to this and to that engineer. And this solves one of the part of the project for debuggability. But this one part, because sometimes exception happens and we have to figure out where was the root cause of this exception. And there is another tool for that, built into Reactor. So debuggability of Reactor improves and improves over the time, which is pretty good. But there is Reactor tool. And basically Reactor tool is another Java agent which let you enable better stack traces. Their printing, it enables you to make them more less overheady, which basically led us to run it in production without any problems. And since this is Java agent, it basically led us to run it at runtime without reloading the system. And once the big stack trace appeared at your runtime, you can attach this Java agent, and it will prettify much better the stack trace, and then you can kind of reproduce this exception and figure out what kind of operators, what it was in the root cause of this exception, for example. So this is another way, but in general, trying to debug reactive streams is pretty bad idea, and I'm not recommending to do that. Use these tools in order to read the stack trace, try to use things like, for example, for project reactor, try to use checkpoint in order to name your part of your stream. For example, this is before parallel, and then during the exception, this checkpoint will appear, and you will be able to understand, okay, it happened before or after this checkpoint, and you can put a little bit more checkpoints, and it will clarify what was the root cause, for example, as well. So this is a few techniques that I can recommend, but in general, yeah, you have to learn it. You have to apply different things, which just a part of just putting the debug breakpoint at your runtime. And this is how we have to work with reactive programming and reactive streams right now. So yeah, this is about debuggability a little bit. Any other questions? Everyone is shy, which is pretty good. But yeah, thank you. If you don't have any questions, thank you for your time. Enjoy your work, and I hope you learned something new during this presentation.
I also would like to personally thank you for letting us hijacking your lunch breaks. Yeah.
Hey.
I have a question I didn't ask because it's Volkan will know a bit more about it, but it's too much for asking.
Sure.
But we use Reactor a lot, and we use it with PubSub, so it's not a really normal